keep in mind that when we deal with the log function, y equals log base a of x, we have a domain restriction that x has to be strictly greater than 0. That means when we go to solve log equations, we need to look at any of our log statements to identify any restricted values that might pop up as part of our solution, meaning we would have to throw those values out. In example 7, we have the log base 7 of x, meaning we have exactly that same domain restriction. X has to be greater than 0. In order to solve this, we can rewrite that log function as an exponential, which would be 7 squared is equal to x, which would tell us that the solution here is x equals 49. Since that value is greater than 0, we know that's a valid solution to this log equation. In example 8, we have the expression 3x plus 7 contained inside that logarithm, so that needs to be greater than 0, meaning that any solution we come up with has to be greater than negative 7/3 in order to be valid. In order to solve, we can apply the same approach that we used in example 7. We'll rewrite this as an exponential problem, as 2 squared is equal to 3x plus 7, which will give us 4 is equal to 3x plus 7. Subtracting 7 to the other side, and then dividing by 3 will give us x equals negative 1, which again is a valid solution since negative 1 is larger than negative 7/3. In example 9, we have the natural log of e raised to the x power. Logs and exponentials are inverse operations of each other, meaning those will just cancel out, giving us a single solution of x equals 9. We do want to make sure that's within our domain or not a restricted solution. In this case, we're taking the natural log of e to the x, telling us that e to the x has to be greater than 0. The range of that function is 0 to infinity, so that statement is always true, meaning we won't have any restricted values as part of that solution. Or that x equals 9 is again a valid solution. In example 10, we're taking the log base 3 of 9. That's not a variable, so there are no domain restrictions we need to worry about. We can go ahead and rewrite this as 3 to the x power is equal to 9. And then that would be true as long as x is equal to 2, giving us 3 squared is equal to 9. In example 11, we have the log base 2 of x plus 7, meaning that x plus 7 has to be greater than 0, or x has to be greater than negative 7. In this case, we have log base 2 and log base 2, meaning we can apply an approach that we used, or an approach similar to what we used with solving exponential equations. If the logs and bases are the same on both sides, that means the quantities contained inside those logs have to be equal. So x plus 7 has to be equal to 11, or x has to be equal to 4. In example 12, we have the log base 7 of x, so x has to be greater than 0. We can use properties of logs to rewrite this as the log base 7 of x to the 1/2 power is equal to the log base 7 of 5 to the 3rd power. Our logs and bases are the same on both sides, so we can simply consider x to the 1/2 equal to 5 to the 3rd power. In order to solve, we would square both sides, which would leave us with x on the left-hand side, and on the right-hand side, that quantity 5 cubed raised to the 2nd power would be 15,625, which is clearly larger than 0, and a valid solution.